and I hope this expression is becoming a bit clear now. You can find that the this one is the form the current we take. Now the maximum value of current is not equal to 1, so that's not the correct waveform for current. But based on this waveform there, we can infer that for the current which is discharging, this is why it's of a form e power minus x. Yep, so it is going to have an exponential decay there. And like we said, we are introducing instead of x a minus t over tau, and tau is nothing but RC. R is the resistor in series with your capacitor, and C is the capacitance itself. And then the initial value, which since it's a decaying function, so you have an initial value. The initial value in that case we found to be E over R. It's the maximum value of current that you can have. So that's why you multiply that maximum value by your e power minus t over CR or tau, then you get your expression for your current. Okay. Now, these are things we've looked at already. So we've seen if you do that mathematically in your own free time, if you start replacing here your RC by 1 tau, 2 tau, 3 tau, and so on. So initially, when you replace by 0 here, yep, so your value is equal to, so e power 0 is 1. So you get E over R means initially your magnitude is 100%, so it is maximum. And then as you start replacing increasing values for RC is equal to 1 tau, 2 tau, 3 tau. If you replace mathematically, you get e power minus 1, minus 2, minus 3. This is what the percentages you get. And like we just said, of the 5 time constants, so 5 times RC, you can assume the capacitor is fully discharged. Like we said, mathematically it's not 0, but you can assume here in circuits we look at later, if you're asked after how much time can you assume a capacitor is fully charged or discharged, it's going to be 5 time constants. Yeah. Okay, now similarly, now when we look at the voltage, remember the current flowing would start at a very high value and then decrease over time to become 0, whereas the voltage across the capacitor would initially be 0 because it's just now it is starting to charge up, and then after 5 time constants, we find that the value is 99.3% of its final value. Like I've said initially, based on the graph we see in Excel, so this is an increasing. It's an exponential graph here, so it's going to be of a form 1 minus e power minus x. So again, your x will be minus t over RC, and then that part, then your bracket is going to tend to a value of 1. But since the maximum value now is E, because the capacitor would tend to charge to the battery voltage, you just multiply that term by E there. Now it will not tend to 1, it's going to tend to capital E. In our Excel sheet, we use the value of 5, and we saw what the final value it was tending towards 5 itself. So if you replace it by E, you get a final value of E there. Yeah. So same comment, if you start replacing your T there by 1 RC, 2 RC, 3 RC, 4 RC, you will get these different percentages you find in the graph. And like we said, after 5 time constant, you can assume it to be fully charged. Okay. Now this one is simply showing what happens when you start increasing or decreasing the capacitance. Since we've seen the time constant, tau is equal to RC, and tau is in seconds actually. When you take resistance times capacitor, so resistance in ohm and capacitance in farad, you multiply these two together, you get a unit which is seconds. You can prove that if you use base SI units. So what is actually that time constant? We've seen after 5 time constants, you can assume the capacitor is fully charged. So it means if you, in this case, you keep your resistance fixed, you start increasing the capacitor. So if the capacitor is small here, because you can see capacitor smallest one is C1, the smallest capacitor would charge quickest because your time constant is the smallest. If you increase now your capacitance a bit into C2, your product RC2 would be 4, so it's going to take more time to charge. And finally, C3 is the largest capacitor, it's going to take even more time. That's what is illustrating here. Yep. So it's simply saying that you can actually decide or design a circuit by varying R, because C also can be played with. You can also play with R. These two parameters will decide how much time the capacitor takes to charge and discharge. I'll be later. So here we're considering charging, we'll consider discharging in a few minutes. Okay. Now, this part is simply saying here, we've discussed the expressions for VC here, for the capacitor voltage and the current flowing through the capacitor. But what about VR here? Because we have the resistor in the circuit. Now, this resistor is very important. If you did not have this resistor here, remember, when the capacitor is starting to charge, we say that the maximum current which we get is actually E over R, the maximum, because this one can be assumed to be short circuit initially. If you did not have this capacitor here, then you can know you can maybe understand what will happen, because the maximum current is E over R. If R becomes 0, Means if you don't have this one here, then the current becomes infinite. It becomes very large current. So if you don't have this resistor here to limit the initial charging current, you have a very large current which will initially start flowing and most likely will damage your capacitor. So this resistor here is very important. So what are we simply saying here? We've understood that your VC is going to E into 1 minus e power minus t over tau. We just written the expression for VC. For IC, we use an exponential decay because the initial value of current is large and it tends to 0. So IC, we said it's going to E, capital E over capital R, e power minus t over tau, a decaying function. Now we are saying, what about VR there? If you want to write an expression for VR, very simple there. It's just going to be, you just apply your Ohm's law, because VR is simply equals to IC times R, and you have an expression for IC. The current flowing through the capacitor IC is the same current flowing through the resistor R. So there's no difference between the expressions of IC and IR. If you take that current IC, which we know the expression is going to E over R, e power minus t over tau. If you take that current here multiplied by R, you get your VR. So it's not very difficult. Yeah? So this is what we are doing here. VR is going to IR times R, but IR is nothing but IC because the same current is flowing. And we have an expression already for IC, which is E over R, e power minus t over tau. You can find that your R cancels out. So the expression for your for the voltage across the resistor is simply e power minus t over tau. And you can see here, we just understood that the initial value for the voltage across your resistor would be E, because there's no potential difference across the capacitor. So all the battery voltage needs to appear here. That's what you find there. And then as your current decays, your voltage across your resistor would keep decaying until at this point there it becomes 0, because all the EMF E would have come across your capacitor. Yeah, so very logical things. And same thing appears here. You're after 1 time constant, 2 time constant, 3 time constant. After 5 time constant, you can assume that the capacitor is charged. No current. Now, some exercises given there to apply all these principles. So you're given a circuit here, for example, with figures now. So I would encourage you to look at them. In that case, for example, if we look at the battery EMF is 40 volts, you have a circuit very similar to what we considered earlier. So at time t0, we put that switch to position 1. It starts charging now. Your capacitor voltage will initially be 0. And the maximum current flowing IC would be equal to 40 over 8K. So it's going to 5 milliampere. So maximum current is 5 milliampere. And then that will decay over time. Important parameter which we need to calculate always is the time constant tau, which is RC. So if you take 8 kilo ohms times 4 microfarad, so you get 32 milliseconds. Yeah, you get 32 milliseconds. So that's your time constant. Okay, so this is the first thing I would do. I find the time constant for the circuit, which is 32 milliseconds. From this point onwards, we know the expression for the capacitor voltage. So E to 1 minus e power minus t over tau. Yeah, so that's the expression you need to write. The E is 40, the tau is 32 milliseconds, and your T, of course, is a variable, and your V is a variable. Similarly, the expression for your capacitor current is E over R, and that's what I said is 5 milliampere, and then E power minus t over tau. So that's very similar. And your voltage across your resistor is simply E to e power minus t over tau, after just saying, and your E is 4. Yep. And there's one question mentioned here: after how much time can we assume that the current becomes 0 and the voltage across the capacitor becomes E? In a way, we are saying after how much time can we assume the capacitor is fully charged? That's what we are meaning by this. Yep. So we say this is 5 time constant for practical purposes. So just 5 times 32, we get 160. Again, the time constant is equal to RC. Just always remember this. Yep. Okay. Now, this part now is about the discharging part. So we've just seen the charging part, and we understood how a transient is. Let's see what happens when the capacitor starts discharging. Now means after the capacitor is fully charged, or even if it's not fully charged, it has some charge in it. If you disconnect it from the battery voltage, that's what we do here. So at some point now, we don't connect it to number 2, because if you connect it to number 2, we actually have a path for the capacitor to discharge through. We are not doing this here. We are simply disconnecting it from the whole circuit. So it's not connected to your battery voltage, nor to port 2 there. It's just open. So what happens? Ideally, the capacitor should maintain the charge it has reached. So if it is fully charged to E, it should maintain that charge E. but in practice there is a leakage path which is through the air. Yep, so it's going to lose a charge. This is what's called R leakage. R leakage is not equal to R here. Be careful. This is your R here. So this path there is the path of leakage. If the capacitor is left in open air, it is through this path that is going to leak. So like we just said, if you again apply the concept of time constant, so capacitor here is C and the leakage path is R leakage. If you take the product of C and R leakage, so the greater R leakage is, it is maybe in mega ohms or very large values, the larger will be that time constant. So the larger it will take for the capacitor to discharge. The larger R leakage is, for example, if you place it in a vacuum, for example, where there's no contact with air and so on, then maybe it will not discharge that fast or not at all. Yep. So in an ideal case, but R leakage there is going to be so large that you can assume it to be an open circuit. In ideal case, your time constant becomes infinite, means it will never discharge. Yep. Okay. So that's what you would get if you disconnect the capacitor from any paths and there's no path for the charge to flow. But if you leave it in open air, the capacitor would discharge over time. It means you have a path for the charge to flow. That I leakage there, it has to flow through R leakage, and that would be through air, through over a straight capacitance path, as we call it. And that R leakage is typically very large. This is why the capacitor would have this circuit would have a very large time constant. Now, if we connect it now to, we don't open it, we just really connect it to path 2 here, as you can see. So when you connect it to 1, the capacitor is charging. That's 1 is charging because connected to your battery. Now, at some point, if you connect it to number 2 here, what happens? So the capacitor is charged, it would now behave itself. The capacitor would behave itself now as a battery source because it has charge on it. So let's see what happens if you connect now to port 2. You can see now the capacitor had a positive charge here, so the current will start flowing in this direction from positive to negative. Yep. So it's going to discharge now through the resistor R. It has a path to discharge. Again, that R is not R leakage, it's the R in the circuit itself. So again, same concept we have. So you have a time constant now, which is again C times R. So you get a time constant. Now, your battery will now start discharging, means your E, your battery voltage would initially be capital E, if it is fully charged initially, and then we tend to go to 0. So it means you can write an expression for VC now because it's now decaying. So the expression for VC would be the initial value is capital E multiplied by e power minus t over tau. That's what's going to be the expression for VC when it decays. Now, current initially would be maximum when your capacitor voltage is maximum, but as your capacitor starts discharging, even that would reduce. So both of these VC and IC would both be decaying functions. But one important difference is if you look at the direction of a charging current here. So the charging current was flowing in this direction. Yep. And now look at the discharge current, it has reverse direction. It has become on the polarity. Okay, so it means when you write the expression for IC, we need to put the minus sign with the expression. Now, same comment, what will be the maximum value of your current initially? For the discharge current, it will be E over R, because the maximum capacitor voltage is capital E and the resistance is R. So initial value is E over R. And since it's going to be a decaying function again, it will be E over R multiplied by e power minus t over tau, but with a minus sign in front because the direction of current has reversed now. For the capacitor voltage, there's no change in potential. It was plus minus here, it remains plus minus. So it's going to be positive always. It would remain positive, but it's a decaying function. So just to summarize this, so everything is discussed there. You can read that when I send the lecture series to you. These are the 2 expressions I've just mentioned. So for the discharging current and the so this one is VR is equal to VC. So the voltage across your capacitor is equal to voltage across the resistor, because these two now, the capacitor has become sort of a battery, and the only other element you have in your circuit is a resistor. So both would have the same voltage across them. Okay. Now the current, like we said, we have a minus sign in front of it. So this is a magnitude only. Okay. You have a minus sign. So this is what we expect to get. Yeah, this is showing the charging, discharging. So this is where your switch was position 1. And then at some time, assuming it is 5 time constant, if you turn on the switch to position 2 to start discharging, and then charging, discharging. So this is how the voltage will look like. Whereas the current, we saw during charging, it started with the maximum value of E over R, and then it would discharge to final value. If at time t is equal to 5t, which is the minimum amount of time you need to wait for the capacitor to be fully charged. Then if you turn on the switch to position 2, like we said, it goes very quickly. So you have an abrupt change here to minus E over R, which is the initial discharging current, and then then the polarity reverses, like we said, and then this will start decaying to 0. And then here again you change it to position 1. So this is showing here position 1, position 2 for the switch, position 1, position 2. And we've seen VR is very similar to, so VR was actually equal to, so this is VR during the charging phase, and VR during the discharging phase, VR during charging phase, discharging. Okay, so all these make sense, and you can easily write expressions for all of these expressions. Like we said, it's a charging one, so it will be our form 1 minus e power minus e over tau. The final value is e there, so you multiply by e. This one is discharging with an initial value of e, so it's going to be capital E multiplied by e power minus t over tau, this part there. Whereas this one, you can see the discharging function for the charging current, so it is e over r multiplied by minus t over tau. And this one is a discharging current, so the initial value is minus e over r, and again this is a decaying function, so e multiplied by e power minus t over tau. Yeah. So this one similarly we've written expressions for this. Okay. Now another example to consider. Yeah, let's look at this one. So after the capacitor is fully charged to 40 volts, so your capacitor is fully charged to 40 volts, the switch is turned to position 2. So this is where it starts discharging now. Find the mathematical expressions for all the different parameters. Yep. So first thing, like we said, you work out the time constants, which is equal to 32 milliseconds there. And then once you know that, you can write expressions for VC. And let's just go to the next slide. So your VC was e power minus t over tau. Just replace the values. Your charging current, the discharging current, sorry, one negative sign with it. Yep. And then the maximum value is e over r, and then your e power minus t over tau. This is how it is. So the maximum value is 5 milliampere, which is e over r. And the resistor value, you can find the resistor voltage, sorry, is just a negative of what you have on P. Yeah, so just have to flip this down. Okay, so if you look at all this, you can just read through now. There are lots of other examples for you to consider. Now, one comment on the example we've just considered. If you look at this one, for example, the capacitor was allowed to charge fully. So it means the switch was allowed to be in position 1 for at least 5 time constants. So what if you did not allow the capacitor to charge fully? You switch to position 2, let's say at 4 time constants or 3 time constants or 2 time constants, so on. So it means the voltage which you would get for the discharge phase would not be E. It's going to be a lower value. That's what you're going to look at next. So this example there. Actually, if you read that, it said find the mathematical expression for transient behavior of the voltage across the capacitor and so on. So this one is straightforward. It's thrown into position 1. So initially, you put your position 1 here. So you connect it to position 1. So you can find here your R is 100 kilo ohm and your capacitor is 0.05 microfarad. If you calculate time constant for this phase of charging, it's 100K times 0.05. So you get the time constant. Okay, so you get 50. You get, I'm just checking, so you get 5 milliseconds. Yeah, 5 milliseconds. Okay, so you get 5 milliseconds for time constant. Now we're saying repeat, if a switch is turned into position 1 at this. Okay, so repeat part A for IC. So you get also one expression for IC. The maximum current you get in that case, we say you short circuit your capacitor. So maximum current will be 10 over 100K. Yep, so you get your maximum current. That's going to be this one. And then it's e power minus t over tau, what's your charging current. Now, next one, find the mathematical expressions for the response VC and IC if the switch is thrown into position 2 at 30 milliseconds. Now, we've just said your time constant here is 100 times 0.05 microfarads, so 5 milliseconds. So you can assume your capacitor is fully charged, means reaches a value of 10 volts after 5 time constants. Is 5 times 5 milliseconds, 25 milliseconds. So if your switch remains in position 1 for at least 5 milliseconds, you can assume your capacitor is fully charged. Now, here it's saying 30 milliseconds. So 30 milliseconds is more than 25 milliseconds. So it means, in this case, you can assume your capacitor has fully charged. Now, this question is asking you, if you put your switch now to position 2, so it's not connected to 3 here, 3 will be the discharge path because then the capacitor can discharge here. If you connect your switch to position 2, there's no path for the current for the capacitor discharge. So this is where you have the leakage path. But the question puts another information, assuming that the leakage resistance of a capacitor is infinite ohms. So if the leakage resistance of a capacitor is infinite ohms, it means it will never discharge. Yeah, we mentioned about that. It's a very large value normally, so it takes lots of time to discharge. But if you assume the leakage resistance to be infinite, it means the time constant is infinite. See all infinite, it means the capacitor would never discharge. Okay, it means what would be the value of VC is going to maintain at 10 volts. And what value would you get for IC? The IC would simply be 0 because no current is flowing in the capacitor not discharging, so IC will be 0. Okay. Now, next one is saying find the mathematical expressions for the voltage VC and IC if the switch is thrown into position 3 at time 48 milliseconds. So what happens here at time t0, you put your position 1, it allowed to charge for 30 milliseconds, so it's fully charged. You remain your switch in position 2 here for 18 seconds, so that 30 plus 18 are 48 milliseconds, then you put it on this position there. That's what the question is asking. So when you put it on position 3 here, the capacitor voltage initially is 10 volts because it didn't discharge at all. Then when you connect it to 3, your time constant is not 0.05 times 100 now because it's now flowing in this path. So it's 0.05 microfarad times 200K. So it's RCs here. You get a new time constant, and now you can apply your expressions. We've just looked at for VC, IC, and VR to write the expressions and sketch the graphs. That's what is described in detail here. So this is what we said for storage phase, the charging phase, the time constant 5 milliseconds. This is expression for VC. This is the expression for IC, charging current. So we found that the maximum value is 10 over 100K. So it's 0.1 milliampere. And then there's a decaying function there. And then it's a discharging phase for starting at 48 milliseconds. Okay, your new time constant is R2 times C, not the previous resistance. So you get 10 milliseconds. This is what your time constant is, 10 milliseconds here. Your initial value for your capacitor voltage is 10 because the capacitor was fully charged, and your current would have an expression with a negative sign, and the maximum current will be E over R2, and so it follows through. So this can be depicted as follows. So this is the charging phase. For after 30 milliseconds, you put to position 2, so it maintains 10 volt because the leakage path has infinite resistance, and then it discharges after 48 milliseconds with a time constant, which is the new time constant. So you can work it out. Now, one comment, you calculated the new time constant to be 10 milliseconds. So it means if you allow the capacitor to discharge for at least 5 time constant, which is 50 milliseconds, the capacitor will be totally discharged. This is why you find after 48 milliseconds, if you add 50, which is 5 time constant, you get 98. So after 98, you can assume the capacitor will fully discharge. Now your IC, of course, is a charging current, then there's no current flowing during storage phase. And then as you switch to discharging, it changes polarity and then decays to discharge. Yep. Now, this example there, I'm just going to explain it briefly, and I would want you to consider it. So a bit more difficult, a bit more complicated here, where you have a circuit with few more elements, and you have a capacitor there. So the charging phase is not straightforward. You have a capacitor here, fine, but what value would you use for the resistance? Because you have to get time constant is RC. The C is 0.2 microfarad, but what about R? So this is where you would need to apply Thevenin's theorem, because we know that if you isolate the capacitor, you remove this, and then you just consider your terminal A and B here, you can work out an ETH and an RTH, and your RTH becomes the resistance. So this is where you would apply Thevenin's theorem. Once you get that, then you apply the same technique we just said. So everything is discussed in detail there, but I would want you to go through that. So you've converted your part where you had the resistances sort of in a cascaded configuration. You've simplified it, all the resistances to an RTH, and of course your E would not be the 21 volts now, to an ETH, yeah, because that's what you would appear across your capacitor, yeah, and the resistor. So this is where Thevenin's theorem becomes handy here. You can simplify the circuit into an ETH and an RTH. Once you get it in that format, same equations. We've seen for VC, for tau, and so on. So this is straightforward. And some questions are asked at time t is equal to 9 milliseconds. What voltage would you get? So you just have to replace your t there by 9 milliseconds, and you get the voltage you would get across the capacitor and the current. So that follows. I don't think you have any problem here. Now, this diagram is interesting here. It illustrates what would happen if you don't allow your capacitor to charge fully. Now, if you just go back here, you find your time constant to be 2 milliseconds. Where is this coming from? It is simply 30k times 0.2. Let's check something. It seems a bit strange here. No, sorry. So during the charging phase, your time constant is 6 milliseconds. During the discharging phase, if you look at the circuit there, the charging phase would be this part, discharging phase would be 0.2 times 10. This is where you get the 2 milliseconds. So during the charging phase, your time constant is 6 milliseconds. So you can assume the capacitor is fully charged after 5 time constants. So 5 times 6 get 30 milliseconds. So it means if you look at the graph there, your capacitor would be fully charged if you allow it to go to 30 milliseconds, but you are switching only after 9 milliseconds. This is what the question is saying. So after 9 milliseconds, if you switch, you need to find what voltage is actually stored on the capacitor. So you just have to apply this equation there, 1 minus e power minus t over tau. You replace your t now by 9, and your tau is of course 6. You get a voltage of 5.44 volts. So it's not your 7 volts, that's fully charged. This is why you get 5.44. At this point, if you start discharging, it means this becomes your voltage across your capacitor, not the 7. You will follow the same steps, but you have to be careful now. You won't use 7, but you would use 5.44. So maximum current flowing now would be 5.44 divided by 10. Yep, this is what you're doing here. 5.44 divided by 10, not 7, because the capacitor was not fully charged. So you have to be careful. Always look at use a time constant to decide what if the time constant exceeds 5 time constant. The time exceeds 5 time constant. You can assume you're fully charged, equal to battery voltage. If not, you will need to use expressions you've calculated, mathematical expressions you derived to find what voltage you're getting.